Hi folks, welcome back to Physics with Quick Captain Rod. The purpose of this video is to introduce a concept called motional EMF. And before we even talk about the concept and what it means, I'd like to talk a little bit about its name. So if you've got me for a physics class, you know that I very much frown upon the term EMF, and a lot of physics people do. EMF stands for electromotive force. What they really mean is motional voltage, a potential difference that you can get in a conductor because of how it interacts with the magnetic field. So really what we're looking at is a motional voltage, or a voltage produced by motion. And again, voltage is not a force. So what we're looking at is we got this region in space where there is some sort of external magnetic field as represented by these, whatever color this is, kind of purplish arrows. This field is described by this vector. It has some magnitude. It's in the -k direction with respect to this set of coordinates I've drawn. Most of the physics that I describe, I use what I call a Zatcha coordinate system, X, Y, Z, Atcha. So this field is pointing into the screen that you'd be looking at. And we're going to assume for this example that this is a uniform field. What we're looking at here is some sort of a conducting block. Now the actual geometry is not important. I'm just trying to use a very simple geometry for visualization purposes. Let's say this block's got dimensions maybe X, Y, and Z. Important to realize though that it is a conducting block. And what I want to chat about here, what we want to discuss, is what happens when this block moves through a magnetic field. So again, all the action is occurring when this block moves through this field. So for the next few minutes, the example we're going to talk about is this block moving left to right through this field. Now I'm going to leave the block right here as I discuss what's happening. But again, we're going to be talking about what's happening if the velocity vector is to the right and this block is in fact within this magnetic field's grasp. Now, this block is made of atoms, no doubt, like anything else, protons, neutrons, and electrons. All of the electrons in this block are going to experience a force in one direction. All of the protons are going to experience a force in another direction. The protons are not free to move. A lot of the electrons are, for all practical purposes, not free to move, but some of them are. If this is conducting material, then its outer shell electrons are very weakly bound and free to move. Now again, even though it's the electrons that are free to move, we normally focus on what's happening to positive charge carriers, because electrical current is normally described by positive charge carriers. So I'm going to draw a picture here of a single positive charge carrier that's somewhere in this block. And the velocity of that charge carrier is to the right, or we would say maybe in the plus I direction. So this charge carrier, as it moves through this magnetic field, is going to be acted upon by a magnetic force, which is given by Q V cross B. So the velocity vector is to the right. The magnetic field vectors are into the page. And if you do the cross product using your right-hand rule, it's kind of tough to show on this computer screen, but with your fingers parallel to the velocity vector, sweep towards the magnetic field vector, which would be in the -k direction, your thumb will point in the direction of the magnetic force. So in this example, the magnetic force is going to be up. And that force will point in the plus J direction. Now, essentially now, every positive charge carrier in this block will feel this force up. Any negative charge carrier will feel a force in the opposite direction, down. And again, those electrons, the outer shell electrons, are free to move. So what's going to happen is we're going to end up with a positive charge configuration on the top of this block and a negative charge configuration on the bottom. Now, it's not that one of these pluses, moved from here all the way to the top. In reality, what's happening is the electrons are feeling a downward force, and some of them are free to move. So down in this region, there is some area that didn't have any electrons, and now it does. These electrons came from the region just directly above it. Up here, there's a region that used to have electrons and now doesn't because some of them shifted downward, leaving us with a positive charge configuration up top, negative charge configuration on the bottom. Right. Now, when we have a charge configuration like this charge imbalance, we're going to have an electric field in the region between these. I'm going to go ahead and draw that electric field vector in, I guess red. So we're going to have electric field vectors now that point down. Remember, electric fields point away from positive charge and towards negative charge. Because we have an electric field vector and we have some sort of distance in that direction, we now have a potential difference between the top and the bottom of this geometry. That potential difference is equal to whatever the electric field is in this region times whatever this displacement is. In this example, that distance would be y. Now, so far I've only talked magnitude. Electric potential always decreases in the direction of the field. So the top of this conducting block is now at a higher potential than the bottom. This voltage that we get between the top and the bottom is created by the motion of these conductors through the magnetic field, and hence it's called motional EMF, or motional voltage. Now, let me go back to this free body here, this picture of a single charge carrier somewhere in this block. Because we have an electric field acting downward, on every charge carrier in here, we now have a Coulomb force acting on it, or an electric field force acting down. This force is going to equal charge times the electric field strength. The original magnetic force given by this cross product is equal to charge times velocity times magnetic field strength. Now, the instant this block hits this magnetic field, the electrons move not in a truly zero sense, not a truly instantaneous sense, but remember that the mass of an electron is 10 to the minus 30th power, roughly. It's 9.11 times 10 to the minus 31st. That means that you put any force on them at all, they react pretty well instantly. Once the electrons shift, this thing is now basically in equilibrium, which means the net force on this charge carrier is now zero. What that's going to do is allow me to take this force, which is equal to QVB, minus this force vectorially, set it equal to zero, and we have an equation here where we can solve for the electric field strength. It's going to end up equaling velocity times the magnetic field. Now, I kind of shortcutted through a little tiny bit of math here. The cross product part, the velocity vector is in the plus I in this example. These magnetic field vectors are all in the minus J. The angle between them is 90, and the sine of 90 is 1. And that's why the QV cross B ends up being just Q times V times B. Right. By combining these two equations, we basically can get now an expression that gives the voltage difference between the top and the bottom of the block. Since the voltage is the electric field times distance, and the electric field is given by velocity times magnetic field strength, here's an equation here that tells us the potential difference between the top and bottom of this conductor. Now, in this example, and again, remember in the original example here, I was talking about this block moving to the right through this field from left to right. So in that example, the top ends up positively charged, the bottom ends up negatively charged, and the top of this block is at the highest potential. If we were to change the velocity direction, maybe we moved this block up through this field. Now the QVB force, or the QV cross B force, would be to the left. The left-hand side of this block would be positively charged, the right-hand side negatively charged, and then the left-hand side would be the higher potential. The important distance then in the voltage calculation would end up being this distance, and so forth. So you can always tell what side of your geometry is at the highest potential just by looking at the direction of the QVB force. as the conductor moves through the magnetic field. And then typically you can get at an expression for the voltage just by drawing a free body diagram of a single charge carrier somewhere in your conductor and writing a Newton's second law equation. So, all right, the purpose of this video is just to be an introduction to the idea of motional EMF. I hope this video has effectively done that for you. Have a great day.